Assalamu alaikum. Let us begin our lectures formally for Module 5. In Module 5, we will cover these topics: curve fitting, linear regression, and interpolation. So, we will begin our discussion in today's lecture with curve fitting. Let us first understand what curve fitting is. Curve fitting is basically the process of finding a mathematical curve or mathematical function that best represents a set of given data points. The main purpose of curve fitting is to theoretically describe any set of experimental data with a model, which is preferably a function. If it is a function, then it has a mathematical equation so that we can describe any given data points more precisely and more logically. And after the curve fitting has been done, uh, we can uh, we can manipulate or we can process the set of data points more precisely or with more precision for our future uses. Here, this is one example of curve fitting. Let's first observe those discrete points. Let's say these points have been extracted from an experiment, and we are given only these data points in a graph paper. So, can we come to any conclusion how these points change over the time, or with the change of temperature, how the value of CCF changes? We might have a very random idea. To have a very concrete idea or a logical point of view of these data points, we need to set a mathematical function that fits the idea of these data points more logically. So for that reason, the process is needed, or the process of curve fitting is needed. Here we have here we have drawn a mathematical function which basically deals with this set of data points more precisely or more logically, and this curve actually explains the set of data points more accurately than any other uh, mathematical function or any other mathematical point of view. So this whole process is called curve fitting. So the next question arises that how do we know that this curve or this mathematical function or this particular graph is best fit for this set of data? So in the next part of our lecture, we will explore those things. We will see how we can define a function, and then how we can find the best form of that function that describes any given set of data points. So uh, as we have discussed, the main idea of curve fitting is that we might be given a set of data points, and uh, our job will be to establish a relationship with a mathematical function that basically. So now we will look at one of the methods that will help us establish a mathematical function. Now we will look at one of the methods that describes how we can come up with a mathematical function that describes best the any set of data. For example, look here. This is x-axis and this is y-axis, and we have 6 data points given to us. And now we would like to establish a mathematical function that will be the best fit for this set of data, and that will be able to communicate to us mathematically. Uh, So now we will look at one of the methods of curve fitting, which is linear regression. Using linear regression, we will see how we can fit a given set of data points with a mathematical function. Here, using linear regression, we will preferably fit our given set of data point with a straight line. And in the next few minutes, we will see how we can come up with the best fit for any set of data or best function that describes the set of data more accurately or more logically. For example, look here. Here we have 6 data points given to us. This is x-axis and this is y-axis. So now we would love to establish a relationship with these data points and a straight line. If I ask you which straight line you would love to draw or you would love to have here that will best describe these data points, some might say a straight line of this order. Okay, this is a straight line that goes to the origin. So if we look further, this is the mathematical equation of this function would appear. Okay, some might disagree. No, I don't like this straight line. I will rather go with this straight line with a different slope because this is much closer to these 2 points. And that is also a valid argument. And some of you might say, no, let's go with this straight line with another slope where we can see that this straight line is more closer to these 4 points. In fact, it is going through one of these 6 points. This is also a valid argument. Some might say, no, we want a straight line of this order, which will be elevated or which will have an intercept from y-axis, which means the straight line will be of this order, and it will be the best fit for this given set of data. Some might argue that no, I want this straight line to move a little lower like this way. Again, some might say no, I want it in this order. So in this way, we can come up with different straight lines, and all of them can have a valid points or valid logical point of view to represent this set of data. As per the main idea, we have seen we can draw different types of straight line to represent this set of data. Now the main question here is that which straight line should we eventually choose? Which straight line is actually representing this set of data more accurately or the most accurately? To understand that point of view, we have to come up with two new parameters. One is error on each points. Okay, so we were given a set of data points and we have assumed one straight line. So obviously the straight line can be of different orders. For example, we are now dealing with this given straight line. See here, the corresponding data points on the straight lines are not actually falling on this given set of data points. So there are some error. To calculate this error, we can easily subtract this given set of data points minus the corresponding point on the assumed straight line. So this will give us error. So and the value of error at each points. Another parameter is needed, that is sum of squared error, because some of the error values will be positive, some of the error values will be negative. If we take square of those error values and take a sum of all those errors, that gives us another parameter, that is sum of squared error. Now, the main idea here is that we would need to choose such straight line where the produced sum of squared error is the minimum. See here, this is one example. So this can be another example. This can be another straight line that we can assume to, which is we can assume it to be the most perfect way to represent this set of data. But look here, for this case, we will have some value of sum of squared error. Okay, For this case, we will also have some sum of squared error. For this case, we will also have some different sum of squared error. So you can already imagine that for these four different cases, the sum of squared error will be different. So now our goal is to establish such a straight line where the sum of squared error will be the minimum, and where the value will be minimum, that is what is our desired straight line, that is what is we are going to pick as the best representation of our given set of data in the form of a straight line. If we sum up what we have discussed so far is that we will be given a set of data points. To represent that set of data points, we are looking to establish a mathematical function that best represent that given set of data points. And for linear regression, that mathematical function will be a straight line. Okay, we can assume one straight line. The next thing is that we have to make sure that assumed straight line produces the least amount of sum of squared error. To visualize this whole thing, I am adding a small clip from a YouTube video. I think that if you look at it, you will be able to visualize the whole thing more clearly.
There's these differences between the points and the line, these little red segments. These are called residuals. They are the differences between the data points and the predictions the line would produce. Take each of these residuals and square them. These are the squared errors, and notice that the larger the residuals are, the more amplified the area of the squares are. If we total the areas of all of these squares for a given line, we will get the sum of the squared error, and this is known as our loss function. We need to find the beta 0 and beta 1 coefficients that will minimize that sum of squared error.
For our case, we need to come up with the values of a0 and a1 such that the sum of squared error becomes the minimum. From our discussion so far, we have seen that this is how the function of sum of squared error looks like, or this is the loss function. And our goal is to find the values of a0 and a1 such that when this loss function becomes the minimum. If we rearrange these statements in mathematical format, which translates into something like this, that we need to take derivative of this function with respect to a0 and with respect to a1, so much so that the derivative returns this value 0. I mean, we are looking to find out the minimum values of s with respect to a0 and a1, or in other way we can say that we need to find the values of a0 and a1 which actually results in the minimum value of s, and the whole thing can be restructured mathematically in this way. The derivative of s with respect to a0 should be 0, and derivative of s with respect to a1 should be 0. So here are our two equations that we need to find the values of. Now let us begin by looking at how the condition of the equation 1 becomes. The equation 1 says that we need to take the derivative of function s with respect to a naught. By taking the derivative of s with respect to a naught means we have to take derivative of this function with respect to n a0. We take this derivative. This is the output we have. Then if we do the due multiplication, we end up having these three terms. From here, we can remove 2. I hope you understand how and why. Let me explain this transition. 2 has been nullified, and we can take the constant out of the summation, and hence this thing can be rewritten as this. And then we can rewrite this term like this term like this, and this term like this. Okay. Okay. Then why we have rewritten this thing as this format? Because it is the summation of a0 means that we need to take a multiplication of a0 with the number of samples given. For example, if we are dealing with 5 values, here we will take the a0 multiplied by 5. This is how this term has come into this position. And if we then rearrange it and keeping the a0 and a1 term at the left hand side and pushing this value to the right hand side, this is the final version of the equation 1. Now let's see what happens to the equation 2. Here in the equation 2 we stated that we would have to take differentiation of s with respect to a1. If we take the derivative of a1, if we take derivative of s with respect to a1, we will be basically doing derivative of this function, and this results in this thing. And if we do the due multiplication, then we end up having these three terms, from where we will strip the value 2 off, and after that we will be left with these three terms. From here we can convert this term into this, convert this term into this, and then rearrange it like we have done for the equation 1. So this is how we can convert our equation 2, and this is the final version of the equation 2 that we will have at our hand. If we place equation 1 and equation 2 side by side, this is what we get to see. So this is a situation from where if we solve these two equations, we will eventually get the values of a0 and a1. How we can get it? Look here, if we rearrange this thing like this way, if we are given a set of data, and from those given set of data we can easily calculate these values, the sum of xi, sum of xi squares, sum of yi, sum of xi yi, and then plug these values here in these positions, and that will eventually give us the values of a0 and a1, which returns the absolute equation of the straight line, which will be able to demonstrate the given set of data perfectly, and which which will be most mathematically accurate. So the discussion here is that using these equations, we will be able to calculate the values of a0 and a1 such that that returns the minimum values of sum of squared error, and having those values of a0 and a1, we can eventually get the equation of the straight line, which best represents our given set of data mathematically. So that was the main idea of our linear regression, or representing a set of data using a straight line. In similar fashion, we can set up a polynomial regression for a given set of data, where we can come up with an equation of a polynomial, or here we can see that we can come up with the equation of parabola, which we can assume to be best fit for the given set of data. If we assume a parabola to be best fit for any given set of data, in that case, the sum of squared error will be of this order. And for the main idea here will also be to make the sum of squared error minimum. For that reason, we need to take derivative of sum of squared reason with respect to a0, a1, and a2, which will eventually result in these three equations. If we can solve these three equations, we can find the values of a0, a1, and a2, which will give us the least amount of uh, sum of squared error, and so that we can eventually find the equation of the polynomial, which is the best fit for the given set of data. So applying the same technique, we can uh, have polynomial regression done for a given set of data.